Student, today I will discuss one of the very simplest part of your course, that is course number 15 and unit 1. And from school level you are learning this acid base concept. We have already studied the most important contribution of Arrhenius regarding what is acid. We have also learnt about the another concept which is very universal, Bronsted and Lowry concept. And also nowadays we are also dealing with the Lewis concept. Now first, let us know what are the course content of this unit. It is a big unit and I can divide it into 3 parts, and all the parts are very important. Today I will discuss the first part, that is the fundamental of acid and base concept. And second part, you have already gone through my video lecture, that is the acidity function. Yesterday you have seen that if I ask you again, I am using the same concept, that for non-ideal solution we can determine the strength of that acid or base or alcohol with the help of this acidity function. And of course I will also discuss in next classes the application of the acidity function, that is also very important. And the third part, again it is a very old concept, because you all know the role of catalysis. But here in this course content, we will study the different types of course, acid-base catalysis. There are 2 types of acid-base catalysis. One is specific acid-base catalysis, another is the general acid-base catalysis. And again in general acid-base catalysis, there are some general acid catalysis and general base catalysis. So, and in addition to general acid-base catalysis, we will learn enzyme catalysis also, the competitive inhibition, non-competitive inhibition. And lastly, we will discuss a very important concept. I do not know whether you are aware of alpha nucleophile. You know large number of nucleophiles for organic reactions, but there are certain nucleophiles that can increase the reactivity of a chemical reaction the million times or the billion times, and that is called the alpha nucleophile. But today I will concentrate only on acid-base concept, and I will not discuss the fundamental definition of acid-base concept, because you all are aware of this, the role of Lewis, whether it is if it is acid, so it is the electron pair acceptor or basic electron pair donor. You know the role of hydrogen ion, but the most important contribution is the role of alpha nucleophiles. Today I will not discuss about this alpha nucleophiles. It is of course in your course, but today I will only concentrate only on the acid base concept. Let me start with again I am just giving one example of this alpha nucleophile, because it is a very simple type of compound which is called the para-nitrophenyl acetate. And if you add simple nucleophile, suppose the rate constant is very slow, But if we add nucleophile, the rate constant will be tremendously increased. But yes, that is the most important contribution of acid-base chemistry. Now, suppose I want to know the strength of this water, and I can ask different types of questions. Let me use this blackboard, board. My first question is that, suppose I am taking again my very favorite aniline. And you want to know the strength of this aniline. Suppose it is B or whatever it is. So what are the methods? Yes, I can monitor the pK, sometimes I can monitor pKb, I can monitor pKbH plus. So how can you distinguish between pK, pKb or pKbH plus? As I just give the same example, that my question is that pKa, because water is an amphoteric type of substance, pK of water. What is the value? Or pKSH of water, which is correct? Or pKa of H3O, hydronium ion, because bare proton, existence of bare proton is not possible. Always it exists in the form of hydronium ion. So now these all types of problem can be solved with the help of modern acid-base concept. So normal method, you know that if I apply the Bronsted system, so it can be ionized. Now again, there are two terminology. One is ionization, another is the dissociation. Dissociation is very old concept. Ionization concept is more suitable. So it is like that. It release a proton, and you, with the help of some method, you monitor this equilibrium constant, and suppose that value is 1.0 into 10 to the power minus 25. Very, very low value. Second concept is that 28. 1 into 10 to the power minus 28 is very, very low value. But suppose second part is also possible, that we can use that aniline, because the amphoteric type of things can react to water, and it will give, if it is a base, so it conjugate acid is produced, C6H5 NH3 and OH. And again, this value is around 1.5 into 10 to the power minus 10 is also an approximate value. So it is also possible. So how can you decide that which method is more correct? Thirdly, what you can do, you can use this conjugate part. That means if I take the conjugate acid of aniline, I can use water like that, or even you don't need water. So it can form C6H5NH2, and it will release this hydrogen, so it can form this hydronium ion. And if I monitor, I will get 2.5 into 10 to the power minus 5 value, approximately. So now you can understand the points. That means you all know precision and accuracy and the use of the instrument. So same thing, here I can write that I have taken simple aniline. So I can write it is a proton donating capacity of the aniline. I can write the pKa, or sometimes it is pKa, same thing. But the values is very, very low value, and it is very difficult to monitor or measure these ionization constant accurately, because 1 into 10 to the power minus 28. I am not saying that this method is wrong. In the second case, because it is amphoteric type of the substance, it can accept a proton from here. So this type of conjugate species is possible, and you can also monitor this system. But again, the value is around 1.5 or 4 in 10 to the power minus 10. So it is also very low value. But in contrary, neither pKa or neither pKb, if I take whatever, if it is an acid, we can take its conjugate base. If it is a base, I can take its conjugate part. And if I compare these three, then I will discuss with the last part, in the activity of the water. So here if I can take the conjugate part, which is, I can call it is also a, if I consider that the proton donating capacity of not aniline, but it is aniline, not aniline, but anilinium ion. So what is the nomenclature? You can write pK of anilinium ion. You can write, just bear in mind, pK of anilinium ion, or pKSH, because I have taken the conjugate part of this thing. So there are two terminology. One is pKBH plus of not anilinium ion, but pKBH plus of aniline. So this is the, so in order to avoid all such type of ambiguities, whether we should use the pK or we should use the pKb or we should use the pKBH, such type of acid-base concept is very important. Now I am giving one or two more example. Then I will discuss the last part, that is the pKa and pKsh and pK of the hydronium ion. So now my second example, again, suppose my question is that write the pKa of para nitroaniline. First question, pK of para nitroaniline. So you can write like that. So because it is pK, so proton donating capacity, we add water. So it ionized, it will form nitro and plus. Now if I monitor its ionization constant K, it is very low value. It is around, I think, 19. 4.2 into 10 to the power minus 19. Can you imagine? And then if I calculate the pK is equal to minus log of K. You all know these things. So it is around 19 bar 460. So 18 point, I think, 16 approximately. Same compound. My next question, that write the pKsh or H of para nitroaniline. So then first you have to convert it into its conjugate part and let the conjugate part to ionize. So and then you are able to answer yourself, no sir, this method is suitable, because if I take its conjugate part, okay, and it will dissociate NH2 and if I use the water. But the most important point is that the value of, will be surprised to know, 4.2 into 10 to the power minus 9 is only 0.99 like that, around 1 K value. So you see, you can understand that of course this method is more convenient. So I think now you can understand what is pKa or pKb, what is pKsh plus or pKbh plus. My last example, I am using my last example. Again, it is a matter of, both the methods are correct, but in one case the value is 4.2 into 10 to the power minus 19. It is very difficult to measure, whereas 0.99 is easy to monitor. My last example regarding this pK, that means you must know that what is pKa, what is pKb, what is pKsh, and there are certain compounds like para-aminophenol. If I take the para-aminophenol and if you change the pH, so depending upon the medium, the nature of para-aminophenol may change. That is also important part. In next class, I will discuss some of the numerical problems. Suppose you are taking 3-nitrophenol in your M.Sc final year classes, we can do this experiment. You take the 3-nitrophenol or suppose 0.05 solution, dilute it and measure its pH. Suppose pH is 4.91. So the question may be asked that how can you calculate the pKa of this 3-nitrophenol? So that is a important question. Similarly, I can take another compound, that is morpholine, dilute it and prepare a solution and measure pH. Suppose pH you are getting 9.2. Then I can ask, calculate the pKbH of morpholine. These are the application of pKbH and pKsh concept. And there are so many methods are also there. Potentiometric method is also there, pH metric method is also there. But my objective here is today's lecture is that you must understand what is pK, what is pKbH, what is pKsh. So that if you understand this, so you are able to answer the very simple question, my first question, the pK of water and pKbH of the water. So my last example, a very well known compound, you know all these things, 8-hydroxyquinoline, very important reagent. 8-hydroxyquinoline. 8-hydroxyquinoline. Hydroxyquinoline. Same question, first question is how do you calculate the pK? Fortunately, you add again water. So it will simply, I think from here, proton is removed and its value is nitrogen. I can slightly so and I think this value is around 9.89 pK. Again, second question, pK SH plus. Now, don't get confused about the S. S may be substrate. If you confirm that is a base, then you can write pKbH. So better use the S, substrate, maybe acid or base, no problem. So better here. And if I find last question, that if I, so then I need the conjugate part. I need the conjugate part of this 8-hydroxyquinoline. So conjugate part. Conjugate part means this is the conjugate part. Again, of course, here is also weight there. So from here, it will release the proton. So you will get the hydroxyquinoline and H3. But again, the value of pK is 5 point like that, 5.1 approximately. I am talking about the approximate. And there is a table that is called the Pearson table. So suppose with the help of this table, with the help of this, the value of pK, you can predict. Suppose if I ask you what is the pK of hydrochloric acid and what is the pK of benzoic acid, You know that benzoic acid, I think around 4.28 or like that. But the pK of hydrochloric acid is like -7 like that. So with the help of, if I ask you a very simple question, suppose I am taking 3 different types of compound, benzene, methane and cyclohexane. Benzene, methane and cyclohexane. You can ask me, sir, which is the strongest acid, strongest species in terms of the pK. So you must know the pK of perlite. So suppose this pK, again I am talking about because this is a very high value, 43. You just compare with the benzoic acid or phenol 9 like that. It is 48, 10 to the power 5 times stronger than this, and this is 51. So the application of this pK or pKbH or concept is that with the help of this pK value, one can throw the strength of that type of the species, irrespective of the acid and basic. Now my last example regarding the water. Okay, so today's agenda is only the fundamental concepts of, there are so many examples available in the literature. So you must know the different values of the pK, calculation of pK and pKbH like that. So my last part is that very important thing, that, and there is a possibility of the objective type question also, and it is a very common question for any competitive examinations. But you must understand the last part of this lecture is the, because water is a universal solvent, you all know, and there is a terminology which is called autoprotolysis, very important concept. You can call it, sir, is it ionization constant Kw of the water? Yes, because if I take water and water, so very school level question, and autoprotolysis is 1 into 10 to the power -14. If I ask you what is the autoprotolysis constant of sulfuric acid, yes, self ionization is possible because it is a very strong acid. So it is sometimes called the self ionization. So H2SO4. These are all the important concept of. So it release one, this can HSO4 negative, H3SO4, and I think if its value is 1 into 10 to the power -14 and pK autoprotolysis is 14 like that, here at 25 degree it is I think around 2.9. But if I take ammonia, another example, autoprotolysis, when you will perform some experiment, so you know that it plus, so it is also self-ionization, but in comparison it is around I think 27 like that, approximately, and all values are of course -50 degree because the ammonia, you know. So this type of autoprotolysis or self-ionization is very important. So in modern time, we should not say the dissociation, but ionization or sometimes ionization is two parts. One is protonation, I should say always protonation, and another terminology is the deprotonation. Protonation means pKSH, like that, and deprotonation. So this is the deprotonation. One is ionization, that is a two part. One is protonation and deprotonation. I have given you many examples. 8-hydroxyquinoline, where the pKa value, and one is 9, another is 5, same thing. I have given another example, but sometimes what happens, you will get some abnormal type of result. Say for example, if I take a compound which is called the benzohydroxamic acid, okay, amide type of compounds, is partially water soluble compound. Partially water soluble compound. You dissolve it, prepare a solution, and determine its pK by simple pH metric method. During our M.Sc first semester, we have determined the pK of benzoic acid by using Henderson-Hasselbalch equation. Very well known chemist Albert Sargent. There is a very good book, Determination of the Ionization Constant. So you will dissolve it just like benzoic acid. If it is not soluble in water, you can use some mixed solvent like dioxin or dimethyl sulfoxide. So naturally it will ionize, and the pK value you will get around 8 to 9. It depends upon the substitution. Okay. So it is very simple. Why? Forget about this hydroxy, think about the benzoic acid. So in place of benzoic acid, I have taken a N-hydroxybenzamide, because dissolve it, take sodium hydroxide, titrate it by Henderson-Hasselbalch equation, you can get the pK value. My next question, because it is a deprotonation technique, because it donates a proton. But my next question, will it be possible for you to determine the pKSH of this compound? So what we need first, we need the conjugate. If it is acid, so we need a conjugate base, because it is, we call it the hydroxamic acid, benzohydroxamic acid, benzohydroxamic acid. So simple pH metric titration will not be suitable for determination of the pKSH, because we need its conjugate part. So we have to add some acid, sulfuric acid, and then monitor the spectrophotometric determination of molecular species and protonated species. So if I write like that, so I need a protonated species. And then of course it will, so it is pKSH, and you will be surprised to know that we will get the pK value around minus 2.1, like that, at 25 degrees centigrade. So it is a very interesting subject, that whether we should use the pKa or pKSH, and the techniques are different. And similarly, when we will perform some experiment in M.Sc final year regarding this, some reaction mechanism, sometimes we have used the dimethyl sulfoxide, DMSO, because it is a very protic solvent and inert solvent, and the autoprotolysis constant is very high, I think 33, like that. So this is the importance of the pKSH and pKBH. So it is always not like that the values of pKSH and pK will be same. In one case, in 8-hydroxyquinoline you have seen, so it depends upon the types of the substrate. One is 9 point like and 5, but here you see plus to minus, it is plus 8 to 9, whereas the pKSH is minus 2.1. So without performing the experiment, it is very difficult to determine the exact strength like that. So my last part, again I am just forgetting the water. So last part, pKa of water. First question, question number 1. Question number 2, pKSH plus or pKBH plus of H2O. Question number 3, pK of pK of H3O. So there are 3 questions. Let me solve it. Today is the last part of this presentation. pK of water, pKSH of water, pK of H3O. Okay, so let me start. First is, generally we take simple H2O because the amphoteric type of thing, react with H2O. So it is just pK because one proton is donating. OH negative. So Ka is equal to, very simple, H3O, OH negative, molar concentration of water. You all know this is a school level question. Everybody is aware of all these things because it is 1 into 10 to the power minus 14, you know, divided by molar concentration 55.5. So 1 divided by 55.5 or 1 divided by 50, around 0.02. So it will give 1.8 into 10 to the power minus 60 is the K. But I am asking you the pK. So pK is equal to minus log of 1.8 into 10 to the power minus 60. So you know that bar 16 and log of is around 2553. So it will get 15.5637, 50.74 approximately at 25. So my first part is over. The pK of water is 15.74. But my second question is that what is the pKSH of water and pKa of H3O. So let me solve the second part. For that, we need a base. Suppose I am taking B. I am doing now this part and this part. First part is over. I am taking a base. Add water. So naturally it will take a So BH plus and OH. So now I am determining the KB because it donates the function. So it will BH and OH divided by KB. B. Now water remain constant. So I can write like that. B is equal to BH, my last part, OH negative, KB. But again, my question is not the determination of B. My question is that determination of pKSH or pKBH, whatever it is, of water. So then we need a species which is pH plus. BH. And we take water. And it will give the pH plus and OH negative. So just undo. So now I can write like that, K BH plus equal to, oh, just a minute. Because KBH, so I should need a pH plus. So we have to determine this water. Because pKBH or SH, you can write even BH also. Same thing, species or base. So it will give definitely V plus H3O positive. Because we are, now you can understand that because when I take the pK, I take the simple part, not B. But when I take the conjugate part, so I have to take its protonated part. Whether it is 8-hydroxyquinoline, protonated part, C-nitrophenol, protonated part, hydroxamic acid, protonated part. So this is a protonated part, it's conjugate part. So this is equal to B H3O positive, because existence of bare proton is very, very rare. So water remain constant. Clear? Now substitute the value of B from this here to here. So I should write K BH plus in place of B, so BH OH H3O OH divided by BH and K. So this BH cancel out. So finally last part is that K BH plus is equal to H3 OH divided by AB. So taking logarithm log of this 10, of course, KBH is equal to, you know that this value is 1 into 10 to the power minus 14. So you can write that log of 1 into 10 to the power minus 14. And if I just denominator numerator, so minus log of KB. You know that minus log of KBH is equal to PKBH. We have to determine PKSH or PKBH or PK of H3O positive. Both are same. Either I am using water and it determines its PKSH of the conjugate base, or like PK of, just now you understand, the aniline and anilium ion. So when I am talking about the anilium ion, so I will write PK of the anilium ion, or I will write the PKSH of aniline. So same thing. So if I just, so it is minus PKBH is equal to PKBH of water, or if you want to write here SH, no problem. So if it is 14 minus 14, here is minus, so it is 14, and minus log PK is equal to PKB. But when I just minus, that means log of, it is actually minus 14 plus PKB. But I have just sign change, so it will be minus PKB. I have already determined the PK is 15.74. So 14 minus 15.74, our result is equal to minus 1.74 is the PKBH of H2. So now you can understand that the pK of water is different, pKSH of or pKBH of water is entirely different, hydronium ion. It is also competing with the sulfuric acid like that, minus 7, minus 3, minus 4. So very, very strong H3O positive, and pKa of H3O is also same, 1.74. So today I have just discussed some of the very simple, or you can call it a fundamental example of pKa and pKb concept. And in my next class I will discuss the other application of this pKa and pKb, and specifically I have to solve some of the, as I have told you, the numerical problems. Take some solution, measure its pH and calculate its pKa or pKSH, and then of course hard, soft, acid base theory, acidity function. I have already discussed the acidity function. Again, in some classes I will also discuss the application of the acidity function, and finally I will discuss the effect of alpha nucleophile, which is a very important part of this topic. So I may conclude that this acid-base concept is very important, very simple, but there are so many new observations. So you have to learn very seriously about this fundamental of acid-base concept, acidity function, as well as the alpha nucleophile. And ultimately last we will see the acid-base catalysis, enzyme catalysis, Bronsted acid catalysis, nucleophilicity scales and other things. Thank you very much.